Hi and welcome to another lesson about basic assembly. Today we are going to speak about some more conditional branching. Objectives of this lesson. You will learn about the compare instruction, which is useful for number comparison. We will understand how to compare unsigned numbers and signed numbers using specialized instructions. The compare instruction, or CMP. We want to be able to compare numbers. We could, for example, use the stub instruction and then follow it by a JC, jump carry instruction, for example. This will allow us to compare two unsigned numbers. Let's look at an example code. This code subtracts ECX from EAX and then jumps if the carry flag is set. It jumps to my label. If the carry flag is not set, this part of the code is going to be executed, and eventually a jump will be taken to the outside label. So basically we have two parts of code, two parts of important code. The first part is here, which is commented by we are here if EAX is greater or equal than ECX. The second part of code is this part. We are going to get to this part of code if EAX is less than ECX. Let's try to understand how it works. First, we subtract ECX from EAX. If ECX is small and EAX is large, no problem is going to occur using the subtraction. Therefore, no carry is going to happen. The carry flag is going to stay 0. So if EAX is bigger than ECX, the carry flag will be 0, and then the jump is not going to be taken, and we are going to be here. And in fact, we have EAX greater or equal than ECX. In the opposite case, where actually ECX is going to be bigger than EAX, the carry flag will be set after the subtraction. And then we are going to get to this part of code. Because of the jump carry my label, we are going to jump to my label and invoke this part of code. However, there is a problem with the sub instruction. The sub instruction overrides our compared values. For example, here, we just want to compare those two values of EAX and ECX. However, when using the sub instruction, we override the value of EAX. Many times, or in many cases, we don't want to do this. We just want to compare two values and affect the flags registers accordingly. We don't want to override our actual values that we compare. The solution is the compare instruction. We could use the compare instruction instead of the sub instruction. The compare instruction is just like the sub instruction, however it doesn't store the subtraction's result. That means that the compare instruction is some kind of simulation for what would happen if we did the subtract instruction. It affects the flags just like the sub instruction, however it does not override any of the arguments, and it does not actually calculate the result. It only simulates. It simulates what would happen to the flags register if we used the sub instruction. So it's a pretty cool instruction. It is very useful to compare numbers. The signature or the arguments of the compare instructions look like this. We always have compare and then two different values. We call them here A and B. Strictly speaking, the compare instruction subtracts A minus B, changes the flags accordingly, however it does not change A or B. as we said earlier, it is very useful for numbers comparison. Let's look at an example. This example is just like the earlier example, however this time we use compare instead of sub. You might not fully remember the previous example, so let's take a look at it. Okay, we can see that here we have the sub instruction, and in the new example we use the compare instruction. The difference is that this time EAX is not overridden. This is very useful. For example, we could use the value of EAX in this part of the code, or maybe in this part of the code. We don't have to recreate it or maybe keep it somewhere else, because compare is not going to change the value of EAX. So it is a very useful instruction. Unsigned and signed comparison. Comparison of unsigned numbers and signed numbers is different. We have already learned about it a bit in the very first chapters, where we spoke about the two's complement and the representation of signed and unsigned numbers. When we are considering unsigned numbers, for example, this inequality is true. This number, which is composed of 8 f's, is the largest possible unsigned number, and obviously it is larger than the number 1. In signed comparison, however, when we consider the two's complement, this number composed of 8 hexadecimal f's is smaller than the number 1. That is because the number 1 is positive, however this number is negative. In the two's complement representation, this number actually represents -1, and we know that -1 is supposed to be smaller than 1. It's a bit strange. We have exactly the same numbers, however in different interpretation of those numbers, in different interpretation of those bits, we get different results. In the first case, we get that this representation, or this chunk of bits, is larger than this one. However, in the signed representation, we get that 1 is larger than this number, made of 8 f's. So, how could we know which method to use in each case? Maybe sometimes we should use unsigned comparison and sometimes we should use signed comparison. This could be sometimes a bit confusing. The answer is simple. It is our responsibility as programmers to know what is the meaning of the numbers that we compare. If the two numbers you compare have the meaning of unsigned numbers, maybe you count something that cannot be signed, then unsigned comparison is going to be enough for you. However, if there is a possibility that your number could be signed, for example, maybe you count something that could be signed, maybe the number that you represent could be, for example, the temperature. The temperature could be negative, and it could also be positive. In cases like this, you should consider using signed comparison. Luckily, we will learn about some specialized instructions for each type of comparison. So, once you know which kind of comparison you want to have, it is just about choosing the right instructions for the mission. Let's begin with unsigned comparison. We would like to compare two unsigned numbers. By now, we already know that we could achieve that by combining the compare instruction with the jump carry instruction. Maybe we could even add the jump 0 instruction if we wanted to check, for example, bigger or equal, or smaller or equal. instead of dealing with the carry and zero flags ourselves, we have some ready-to-use instructions. We have those 4 instructions: jump below equal, jump above, and jump above equal. These instructions are suitable only for unsigned comparison. That means that if you compare 2 numbers and then follow them by one of those instructions, the underlying meaning of it is that you consider your 2 numbers to be unsigned. I should probably remind you at this point, although you probably remind it yourself, that the processor doesn't know and doesn't care about the meaning of the numbers that you store inside the registers. The processor only sees the bits. You, as a programmer, should choose yourself which instructions to use. If you choose one of those instructions, the underlying meaning of it is that you think about the numbers you compared as unsigned. How do these instructions work? So we have here a simple table that shows the instruction in one side and the condition being checked in the other side. You should be already familiar with these conditions for checking unsigned comparison. For example, you might have thought about them or seen them in one of the exercises so far. The first instruction, jump below, is just about checking the carry flag. It checks if the carry flag is set. If the carry flag is set, the jump will be taken. The next instruction is a bit more complex. It is called jump below equal. It checks 2 conditions at the same time, which is very efficient. For example, if you had to check those 2 conditions yourself, it could take you more than 1 instruction. However, the jump below equal instruction does it for you. It checks 2 conditions at the same time. The jump below equal instruction, or jump, will be taken if the carry flag is 1 or if the zero flag is 1. And it's not very hard to understand. If we believe the first one, the jump below, which happens when the carry flag is 1, then jump below or equal is just about adding the or zero flag equals 1 condition to get the E, the equal. The other instructions are just the opposite of the first 2 instructions. Jump above is about checking that the carry flag is 0 and zero flag is 0, which is just the opposite of the jump below equal instruction. If you know a bit about the Morgan laws, then you should know that the opposite of this statement is exactly this statement. And the last one, jump above equal, is just the opposite of jump below. So we just reverse this condition and we get carry flag equals 0. You have probably noticed by now that jump below is just a different name for the jump carry instruction. And jump above equal is just a different name for the jump not carry instruction. We are talking about those 2 instructions. And indeed, the encoding of jump below and jump carry is exactly the same, because they actually do the same thing. These are just different names for the same encoding. The same goes for jump above equal and jump not carry. Let's look at an example. You probably remember the first example that we have talked about. We already changed the compare. If you remember, there was a sub instruction here, and now we use the compare instruction. We want to go further, making the the example even more readable. So we can use jump below instead of jump carry. I'll remind you from the previous slide that jump below is just a different name for jump carry. So it shouldn't really matter. However, it does matter for you as a human being. When you say this kind of code, jump below, you know immediately that what we actually do is comparing two numbers and then checking if EAX is below ECX. However, in this example, it could be a bit trickier to understand what happens. We make the change from this example to this one by just changing the jump instruction. The right example is a bit more readable. However, there is no change in behavior. Those two examples are exactly the same, and they will be encoded to the same numbers. The processor cannot distinguish between those two examples. However, this one is more readable to human beings because this instructions says something about the meaning that you give to those two numbers, EAX and ECX. I recommend to use this kind of code over this kind of code. Let's talk about signed comparison. Signed comparison could be a bit trickier, as there are more cases to consider. I mean by that in the unsigned case, we just have small numbers and big numbers. However, in the signed comparison, we should also consider positive numbers and negative numbers, which multiplies the number of cases. We could use compare and then check ourselves the sign, overflow, and zero flag. Each combination of those flags will have some meaning regarding the result of the comparison. If we think for a moment, the combination of sign, overflow, and zero flags is a total of 3 bits, which is 8 options. This is pretty much, and those 8 options should map eventually to only 1 bit, which is about bigger or smaller, or maybe greater or less. Instead of dealing with all those combinations of flags ourselves, which could be cumbersome and maybe even error prone, all this not talking about very hard to remember, we could use some ready to use instructions. Just like the unsigned comparison case, we have exactly 4 instructions to be used with the signed comparison. They have similar names, but a bit of a different formulation. The 4 instructions are jump less equal, jump greater, and jump greater equal. I want to remind you that in the unsigned comparison, we used different words. We used jump below and jump above. Here we use jump less and jump greater. You should remember that jump above and jump below is about unsigned comparison. And on the other side, jump less and jump greater is about signed comparison. This is pretty important to remember. How do these instructions work? This time we have some really strange conditions being checked. At first sight, you might be surprised looking at those conditions. Take a second or two to check out the conditions being checked in each of those instructions, as shown in this table. Good. Basically, we can see that the use of the zero flag is mostly the same in the signed comparison and in the unsigned comparison. You probably can recognize some kind of similarity between this table and the unsigned comparison table. We can also see, for example, that this instruction, jump greater, is actually the opposite of this instruction, jump lower equal. And we can also see this reflected in the conditions. This condition is actually the opposite of this condition. If you know a bit about the Morgan laws, this should be obvious for you. Also, the jump greater equal instruction is the opposite of the jump less instruction. And this is also reflected in the conditions being checked. This condition is the opposite of this condition. About the equal, we can see, for example, that the only difference between jump greater and jump greater equal is that jump greater has this additional condition to make sure that equality doesn't happen. It just checks that the zero flag is not set, which means that equality must not happen. And the difference between those two is that this condition is added. Equality becomes possible because we allow that the zero flag will be 1. This would be enough for this condition to happen. Basically, because we can actually understand the relations between all those instructions, if we manage to understand only one of them, we can understand the others. Maybe mathematically speaking, if we can prove that one of those work, by the relations that we already understand between those instructions, we would know immediately that the other instructions do their job correctly. Maybe the biggest question here is, what does sign flag equals overflow flag mean? What does it actually mean? This is a pretty strange condition to check, because there is no obvious relation between the sign flag and the overflow flag. This is something interesting. There was some thought behind this condition.